I will first introduce the frame in which the project was developed. Voilà. It was developed within the Swiss Territorial Data Lab, STDL as abbreviation. This is a Swiss initiative funded by the Swiss Geoinformation Strategy. Right, yeah, I'm told sometimes you have to. Okay, and so it's funded by the Swiss Geoinformation Strategy. This is a measure to encourage innovation within the public administration, and it is also complemented by the resource of the federal offices, the cantons, and the cities. We have three main missions at SDDL. One is to improve the collective innovation between the cantons and the federal offices, but also to add value to the territorial data through the geodata science and bridge the gap between the research results that we heard a lot of today and the concrete problem of the public administration. How do we work? We work in a co-creative way. This means that the public administration bring their domain expertise and we bring the geodata science expertise. And since 3 years, a nice dynamic established. We have several projects developed with different entities, but today we focus on the project developed with the canton of Jura. This very new canton in the Switzerland, in the northern western part of Switzerland. I'm from this canton, then I'm happy to introduce it to you today. What is the context of the project? So in 2018, there was a very big heat wave and drought, and in 2019, first damages were observed on the beech trees. And from 2020 and on, more heat waves, more drought led to more damages. This is how it looks like. So from the healthy stages of a live tree, so green tree crown, dense foliage, then the unhealthy stage of dieback with some dead twigs already visible, transparency in the tree crown, and finally, when the tree is totally dead, the dead branches have already fallen. Then our goal is to produce a map that can help the planification of felling or the estimation of damages for the politics. And so we developed our method in this study area in the very northern part of the canton. This is one of the most affected regions by the dieback. The Forestry Service collects a ground truth to train and validate the method. It's like more than 200 beech trees with health state, healthy, unhealthy, dead. At the same moment, we acquire LiDAR, point cloud, and aerial images. They have a 3 centimeter native resolution, and we derive the true orthophoto. In the project, we are also including time series from Sentinel-2. This is very important to have the story of the dieback within our model. I will slowly, or fastly, go through the 3 sources of data and see which descriptor for the health state we can get from them. From the LiDAR point cloud, we wanted to have structural parameter. This means that we want to go from the 3D information to a 2D level. Here, a raster cell of a 5-meter grid. And within each of these volumes, we computed 11 different structural parameters. One of them is this canopy coverage. It's computed based on the percentage of first return of the LiDAR above 2 meters. We can see, for instance, here the opening of the forest due to the dieback, represented here in red. Okay. With the satellite images, we didn't do the process ourselves, but we took over a project developed by the HAFL and the BAFU, the yearly variation of NDVI, available and visuable on waldmonitoring.ch. So the NDVI quantifies the health of the vegetation with the near and the red bands. And here what they have done is that they compute a maximal NDVI in summer, and they then compare this maximal NDVI from 1 year with the maximal NDVI from another year. Here, between 2018 and 2017, we can see in red a strong decrease in NDVI, But in comparison between 2019 and 2018, the NDVI value goes back to the normal. So it's really interesting to see here the first drought happening. And maybe we took the time series from 2015 to 2022. And finally, with the aerial images, we wanted to go a step further, a level more precise, and work at the tree level. How we can do that? For that, we have the LiDAR point cloud, in which we can find the trees by segmenting this LiDAR point cloud. We also do some manual correction for the trees in our ground truth. This is this yellow line, the tree crown. And you see also here the black. This is masking all the pixels at a height lower than 20 meters because we want to focus on the tree crown and not take into account the reflectance from the understory. Often the understory is in a good health because in the shadows and benefiting from the situation. And this led us with this area, for instance, for these trees, on which we can compute statistics on the pixel, mean, standard deviation for each band, and the NDVI for each tree. And with all these descriptors, with the health state in the ground truth, we can train a random forest model. Back to the roots. And here the results of our training on the test set. You can appreciate here the overall accuracy, so the percentage of correct prediction in our test set, 79%. It's even better only for the dead class, and we see here that the difficulties between healthy and unhealthy trees, this is also where we have the confusion, the most errors. And the descriptor participating to the model are this yearly variation of NDVI between 2018 and 2019, so this first drought event. We also have the mean NDVI and the standard deviation of the blue band on the aerial images. We really see the dead twigs well on these 3 centimeter images. Then it is reflected and of importance in our model. And finally, the LiDAR reflectance and the standard deviation of the canopy cover also participates to the model. And we were satisfied enough to go for the inference on our study area and get a health map. This is an illustration, so green, healthy trees, yellow, unhealthy trees, red, dead trees. You can appreciate some homogeneous region, but also heterogeneous region. This is why it's important to have tree-level information, because some individuals react better than others to this drought event. There is some genetic here playing a role. Here, a zoom on the map. You can now appreciate the hue in each color, from dark to light. And this reflects the vote fraction in the random forest model. This is the agreement of all the decision trees within the random forest. And it could indicate the prediction which one are most likely to be correct, and maybe the one that have to be checked on the field, or okay, maybe let's see if it's really the reality. Here, an illustration of our validation visit on the field with the Forestry Service. They have also a tablet. We could display the map. Here we recognize these very dead trees. And this was a very affected region because all these areas here are the understory not included in the prediction. Well, this is our main conclusion. We have here a first product which can provide a mean of planning and action for the Forestry Service by location of the damages or estimation of the damage volumes. And the expected performance is like 75, 79%. And now you think, before she only talked about the 79%. It's because if you took another partition of the data set in train and test set, you may lose some of this few percent. And this is because these symptoms of dieback are really difficult to describe in the descriptors. Maybe we should include some more descriptors. Maybe we should also look for more samples for our ground truth. This could be some outlooks for further work. I'm finished, but If after the meal you still want a healthy intellectual dessert, come to see me at the poster session, 1 to 2 o'clock up there. So I will be happy to give you more information about what we've did. Thank you.